Hello, thank you for joining me. This is Robert Rogers, Senior Advisor for Food Safety and Regulation with Mettler-Toledo Product Inspection. This webinar we're going to talk about is complete glass-in-glass detection with X-rays, a short presentation that will provide an understanding of things to consider when inspecting glass containers for contamination. Our format's pretty simple. We'll find out why X-rays are used to inspect products, look at why manufacturers choose to use glass packaging, challenges in inspecting glass packaging, and learn some X-ray basics and provide an understanding for selecting the right inspection system, and hopefully provide some time for some questions. For over 20 years, food manufacturers have been using X-ray inspection systems to ensure the safety and quality of food. X-ray inspection is exceptionally good at detecting high-density physical contaminants. It's also a great tool for protecting brand values. As well as catching contaminants, X-ray inspection can simultaneously run a wide range of inline quality checks that make sure food reaches consumers in the condition they expect. No other technology can do so much for protecting safety and quality. Nowadays, it's not enough to merely say you take product safety and quality control seriously. You have to prove it. With retailers, brands and reputation depending on the delivery and completely safe products. To know more about manufacturers' packaging safety processes and product safety is now a big business. Many well-known brands have already integrated product inspection systems into their production lines to demonstrate due diligence and guarantee their products conform to the highest standards. There are no legal requirements on manufacturers to use X-ray inspection, but there are many national and international regulations and legislations, as well as standards set by retailers relating to food safety, which put the onus on manufacturers to establish reliable product inspection programs. Some retail standards will actually demand that there are provisions for physical contamination protections. Increasing production line speeds and consumer expectations put the pressure on food manufacturers to adopt more and more reliable methods of product inspection in order to ensure their product safety. So why use glass? Made from all natural, sustainable raw materials, glass is essentially to modern life and the only packaging material rated XRays, or generally regarded as safe. With retailer sector striving to be eco-friendly, glass is rising in popularity due to being relatively inexpensive and 100% recyclable. No other packaging material matches the shelf impact of glass. The clarity, shape, and the feel of the glass containers contribute to the premium perception of products ranging from fine perfumes to liquor to food to beverages. In addition, research demonstrates that 70% of consumers believe glass packaging suggests quality. Despite its popularity, glass packaging poses a significant safety risk, and the effect of glass-in-glass contamination can be highly damaging. Evidence show that consumers are much more likely to lodge a complaint about a glass container within a glass container, or a glass contaminant within a glass container, than they were if to discover a chicken bone in a chicken-based product. A tiny fragment of glass can cause serious injury to a consumer, and the subsequent adverse publicity, particularly if a baby or a child was severely cut, combined with the high cost of product recalls, can have a devastating impact on a business. Not only do product recalls mean lost revenue and a damaged reputation, evidence demonstrates that manufacturers' greatest asset, their brand, may never recover. Impurities in the glass itself, such as metal contaminants from aluminum screw caps or fragments of denser Pyrex from recycled domestic glass, will affect contamination detection. Glass is made from readily available domestic materials such as sand, soda ash, limestone, and cullet, the industry term for furnace-ready scrap glass. These components are mixed or batched heated to a temperature of 2600 to 2800 degrees Fahrenheit, and then molded into the desirable shape. However, the process used to produce glass jars creates variations and inconsistencies in form. While the overall weight and outer shape of the jar remain constant from the mold, the thickness of the glass walls, and particularly the distribution of the inner raised base can vary as much as 20%. This makes contamination detection challenging. In addition to other physical anomalies such as molten beads or inner strands of glass known as bird swings, this causes risks and challenges for inspection. The more complex the shape of the container, the more challenging it is to inspect. Round containers are relatively easy to inspect. This is because they have no sharp edges. They have the vertical edge profile, which could produce blind spots. The hard, dark edges where detection would be reduced. Additionally, there can be constant presented as they have no orientation effect. Square and rectangular jars need to be presented or guided well. Oval containers are difficult as well. They're hard to guide and therefore not ideal for X-ray inspection as the image is constantly varying. Embossing on the glass creates a higher absorption area and requires exact repeatable presentation. So the more round the jar is, the easier it is to inspect. Square and odd shaped jars are more difficult because of their presentation to the X-ray itself. The type of product being inspected is also has an influence. The viscosity of that material. Based on the viscosity is really where the glass contaminant is more likely to be. A higher viscosity product, it's more likely to sink towards the bottom. However, a thicker product, it may end up in the body area. Inspection of a cold fill or semi-solid or even a thick particulate can also hold contaminant as well. We also have to be concerned about potential air gaps in the filling process. The more consistent and solid the filling is, the easier it will be to inspect. So basically, a little bit about X-rays. X-ray are part of the invisible a form of electronic radiation. Like light or radio waves, they're part of a single continuum known as the electromagnetic spectrum. Since X-rays have short wavelengths, they can pass through materials that are opaque to visible light. In general, the transparency of a material to X-ray relates to its density. That's what makes X-rays so useful in the food industry. The denser the material, the fewer X-rays that will pass through. Contaminants show up under X-ray inspection because they absorb more of the X-rays than the surrounding product area. X-rays used in food inspection systems should not be confused with radioactive materials such as uranium. Radioactive materials are physical sources of radiation. They emit radiation in the form of alpha particles, beta particles, and gamma rays, and they do it continuously, which is why they can't be switched off. The only way to contain radiation from those radioactive materials is to encase the substance in a substance that absorbs radiation. X-rays, on the other hand, are a little bit different. They act more like a light bulb. They can be turned on and off at will. Switch off the electricity supply to the X-ray system and the flow of X-rays ceased instantaneously. An X-ray system is a radiation-producing device, so let's talk a little bit about the safety and put radiation dose into perspective. The average human, natural background radiation contributes to about 2,400 microsieverts of radiation in a year. This typically far exceeds the radiation exposed from the radiation or from an X-ray inspection system used in the food industry. The typical maximum dose rate immediately adjacent to an X-ray inspection system is less than 1 microsievert an hour. Naturally occurring X-rays come from outer space. Our daily dose is small because the atmosphere filters most of it out. The filtering effect declines with altitude. In fact, those who fly absorb more X-rays than those who stay on the ground. Airline cabin crew received almost double the radiation dose of people who spend their lives on the ground. Legislation also limits the annual leakage from an X-ray system to 1 millisievert a year, which is less than half the average person's annual dosage from natural background radiation, which is 2.4 millisieverts a year. So there's also some confusion around X-rays and food irradiation. There's scientific evidence to show that X-rays do not harm food. In a 1997 study by the World Health Organization, confirmed that food radiation levels up to 10,000 sieverts do not affect the food's safety or nutritional value. That means that foods in the survey were subjected to radiation doses around 10 million times as strong as those used in X-ray inspection. It proves that the food remains safe to eat and that it doesn't lose any of its nutritional value. Food that passes through an X-ray inspection system spends only about 250 milliseconds within the X-ray beam. During that short time, it receives a radiation dose of around 200 microsieverts. The levels are so low that organic food can be subjected to X-ray inspections with no diminution of its organic status. Whichever way you look at it, food that has passed through an X-ray inspection system is good as tasty as it was to eat before it was scanned. There's no measurable changes in flavor, texture, or nutritional values. Food that has been X-ray is undistinguishable in every aspect from food that isn't. As the product passes through the X-ray beam, very similar to when you go to a doctor and get an X-ray of a broken limb, the doctor is going to analyze that X-ray to determine whether or not there's any issues. The X-ray inspection for food and beverage is just the same. The product passes through the X-ray and an image is created. The software then analyzes this image to determine whether or not there is any presence of a contamination. You can see in the image here the pixels where all of the X-ray energy was able to reach the detector. The image is very light and bright. In the darker areas, even around the surrounding edges of the package, you can start to see a darker tone within the pixels. That indicates that less of the X-ray energy was able to reach the detector. Through to the most dense areas of the package, which would be the darkest pixels. If contamination were present, even more of the X-rays would have been hindered from reaching the detector, and therefore the pixel in that particular area would be very dark. In X-ray inspection, it's really all about densities. When we talk about densities, we talk about the specific gravity of a material. Here we see a chart that has some contamination potentials listed. Things such as hair, insects, wood, certain types of plastic like polypropylene and UHMW. For the most part, those are very challenged to be inspected and detected within an X-ray inspection system because of their lack of density. So there's programs that we certainly have in place to protect against those. We wear hairnets when we walk into the production environment. There's good pest control programs to prevent insect infestation. We are no longer allowing wood on the operations floor. It's because those materials are very challenged to be detected in any kind of technology today. Certainly the future may hold some differences in abilities to detect those materials, but for now, recognized inspection systems are very challenged to inspect those materials. You come down into the materials that are detectable, a type of plastic like PVC. PVC has an attribute in it that makes it more dense. So therefore, what some plastic manufacturers are doing is they're starting to place additives within certain plastic materials to make them more visible in either an X-ray or in some cases even a metal detection capability. Come down into some of the more unusual contaminants like bone, stone, and glass. Here you can see the specific gravity of glass is very closely related to the specific gravity of aluminum. Those materials have similar densities. You would see on a periodic table of elements that they sit right next to each other. Whereas the other materials that make up the other metals like iron, steel, and stainless steel, they're more closely related on the periodic table of elements, and that's why they are so closely related in their specific gravity. So X-rays can't necessarily find everything, but they certainly can find the majority of contaminations, and in our case, we're concerned about the glass and glass capability. Here you see on the periodic table of elements, we have, I'll just turn my whiteboard on accidentally, sorry. We have aluminum and silica, number 13 and 14, sitting right next to one another. Aluminum and silica. Silica is what they make a lot of glass out of. Come down here where you see the chromium, nickel, copper, those type materials, the ferrous metals, those materials are what make up the majority of our other metals, and you can see they are more dense than what the silica and aluminum are. So it's important to understand that when choosing the right system, you want to have the best glass and glass detection capability. The inspection equipment alone cannot solve contamination problems unless each element from beam angle to reject mechanism has been chosen to fit the line and the product. Various X-ray systems are available for glass and glass detection. Here we can see a single beam application. The single beams are challenged because they have only one perspective of seeing the product. As the product passes through the horizontal X-ray beam, the generator is positioned in only one location. So in this area, you can see at the base of that product, that would be included within some of the masking of the package material itself and make it very challenging to identify. With a split beam, the probability of detection can be improved. The single X-ray only allowed one perspective and view of the jar as it passed through. Having multiple beams, we get multiple views of that jar as it passes through. You can see in this side, the split beam, each image represents a different viewing angle, thus increasing the coverage of the inside of the container. Contaminants located on the sidewall in one image appear nearer to the center of the pack than on the other image, making it easier to detect. A fragment of glass is never a perfect cube or sphere. It's sharp, irregular shape. The more the contaminant lies in the path of the X-ray beam, the more product is displaced by the denser material, which makes it easier to detect. Therefore, inspecting the same jar simultaneously from two different angles increases the chance of the shard detection. With using multiple horizontal beams due to the angle between the beams, it's important to allow the adequate product spacing to ensure that each product can be independently inspected. Sometimes scrolls or star wheels will be needed to ensure the gap is created between the packs. Combining of a vertical and horizontal beam is the next step for increasing coverage and optimizing the detection in more difficult areas. These are available to food and pharmaceutical industries with Optimum X-rays using the vertical beam and 3 horizontal beams simultaneously. This can significantly reduce the blind spots, increasing the machine's capability. Machines are also able and capable to position the generator vertically to inspect a wide range of different container sizes versus the neck of the jar. In addition to providing unrivaled glass and glass detection, X-ray systems are simultaneously capable of monitoring fill levels and headspace, identifying damaged packaging, and detecting agglomerates or clumps within the product. This helps the manufacturers avoid product waste, but the ability to measure headspace can also prove useful when filling liquids, such as sauces or jars of vegetable that rely on a specific amount of liquid within the container to maintain product freshness or to preserve the product shelf life. For example, if a container is overfilled with vegetables in the first phase of filling, there will not be enough headspace for the right amount of liquid needed to preserve the product effectively, leading to premature spoiling. By measuring the headspace, the X-ray technology can help to avoid that product spoiling. Testing the system is always a challenge as well. With X-ray inspection, essentially any part of a well-designed system should include a testing protocol. To guarantee accuracy and reproducible results when using test samples, the density of the glass sample should be known and compared to the density of the container glass being used on the production line. Problems may arise if high-density glass sample is used for testing, but the actual glass in the bottles used on the production line are lower density glass. In this case, the glass test pieces would be detected, but not the container glass, giving the false unreliable results. Good practice is to use soda-lime glass. It's the most prevalent type of glass and closest possible to domestic glass container glass. There are various regions within the glass container that could contain the contaminant. The detection of glass in the location needs to be verified. The figure shows 5 locations in the jar where detection has traditionally been proven to be most challenging. Although in theory the test sample should be placed in each area, in practice it's not feasible to make up such a complex jar. It's recommended therefore that producers and packers of products in glass containers primarily check in the corner of the base and on the side walls in the base of the body. So in conclusion, glass package is rising in popularity. The risk of glass and glass contamination and its highly damaging effects, combined with increasing stringent safety regulations, means it more and more important than ever for manufacturers to have X-ray inspection systems that offer the most sensitive product inspection. The base of the glass jar has traditionally presented a challenge for X-ray inspection systems. However, innovations in technology mean systems are now available, offering all-around inspection in a wide-ranging portfolio of food, beverage, pharmaceutical applications. Choosing the right system is fundamental. X-ray inspection equipment alone cannot solve the problem, unless each element, from beam angle to reject mechanism, has been chosen for the product. We at Mettler Toledo are happy to provide product inspection solutions to ensure your product safety and quality. We also offer an abundance of educational-focused important material, such as literature, white papers. So please visit our website for further information. I hope this presentation was informative. I thank you for the opportunity. If we have some time for some questions, I'll answer the questions. I see in the sidebar here, we've got a question. What is the safe glass threshold? Minimum glass particle size that allowed that causes no injury? Well, that's a little bit of a tough question, but there are very few standards and regulations that actually go to the point of classifying a size of any material for contamination that would be considered a hazard. There is some guidance through the FDA. They have a guidance that talks about hard and sharp objects as a potential choking hazard, and that would be material that is 7 millimeters in diameter or 25 millimeters in length. However, certainly any size smaller than that could be seen as a potential hazard, certainly depending on the portfolio of the consumer. An example would be baby food, or babies consuming baby food from a contaminated glass jar. There is some guidance through the Canadian Food Inspection Agency, where they have specified in some cases a 2 millimeter standard for physical contamination. But in many cases, it's really up to the manufacturer to determine what is a hazard. There's little guidance from regulation, and certainly no specification that I know of within any of the GFSI type related programs specifically stating a contamination size for any contaminant, let alone focusing in on glass.
Okay, Robert. Yeah, that question actually was posted by Susil Fernando. So yeah, thanks for answering that. Should we switch our webcams on so the audience will be able to just see you for a little bit, and we'll stop sharing that presentation. Just before we stop sharing that presentation, on there, as you can see, there's a whole wealth of information on the Toledo website. You know, in-depth articles and white papers, webinars. So you can see, just head over to mt.com. Right, let me stop sharing the slides. And then we do have just one other question, and that was from, let's see that. That was from Mel Morris. And that, as you can see there, we're beginning to think about vision X-ray equipment for our whiskey and other liquors. You know, how would we get started? Sort of where to begin?
Yeah, there's, I mean, really going through and evaluating the various hazards throughout the process. In that application, I'm sure there's several stages of filtering and things of that nature. So a lot of contaminants, the likelihood of contaminants at that point in the process would certainly be reduced depending on the mesh size of the filtering systems. In many applications, the filler nozzle itself would limit the size of contamination that would allow to pass through, and you typically end up with the filler nozzle clogging and creating a lot of other chaos in the production environment. Probably the biggest risk is from either the glass container itself. I'm sure there's probably some sanitation stage where that container is sanitized and cleaned out, and maybe even inverted to help eliminate any kind of debris or you know, gunk that may be in there. Again, the capping process it tends to be where the biggest area of risk is, when the cap is misaligned and you get damage from that part of the application. The other challenge in that industry are the production speeds. Typically, the throughput rates are extremely high, and the fragile product. So if we do determine that there's an issue with that particular bottle, removing that from the line without causing further chaos and glass breakage, if you will, within the production environment. We could always come out and look at the process, learn more about the process, and give some ideas as to what may be the best applications. Certainly happy to help. If you jotted down my email address there, shoot me an email, and I'd be happy to come out and take a look for sure.
Do you know, rather than just a question from me, really, Robert, rather than like rejecting, sort of pushing it off the line or into a reject area, is there a way to mark bottles like with an inkjet or a label or something at high speed?
There is some things that people are doing in that regard. You know, I don't know necessarily from that particular application, but in regards to marking rejected product and identifying it by that, yes, I have seen some applications where they do that. Don't really personally have a whole lot of experience in the you know, in the liquor side of the business to fully understand how that process works. But you know, it's something that I commonly do is just go out to a facility, trying to understand their challenges, what they got going on, try to better understand the process, and then give them some ideas to possibly improve the process.
Yeah, I guess everything, yeah, every process is unique, really, and
it really is. Yeah.
Okay, Robert. Well, they're the questions we picked up that were submitted prior. I know if this was live, there'd be a lot more, and I think probably we will get some on the day. So what I'll do is I'll collate them and forward those to you, and hopefully we can pick up them on the later day. But for now, Robert, thanks very much. I hope to see you again soon. Cheers. Thank you.
It's always good. Thank you, Simon. We appreciate it.
Cheers.
Thanks for joining us, everyone.